Hi, grade 12. It's time for physical sciences. My name is Tinyiko Kosa. We are going to have a lesson based on mechanics, and this is some of the work that you did in grade 11, but work that is important for you to know at your grade 12 level. We will be talking about mechanics, and we'll be looking at a number of things, including force and how it causes motion, and a whole lot of other stuff and topics based on motion. Let's just have a look on the outline of the lesson. Now here we will be talking, like I said, we'll be talking about force. We will look at its effect on motion. We'll be talking about basically motion in a straight line, and we will be looking back at what effects what effects of force on motion, what effects does force have on motion? That's what we'll be talking about. And let's have a look at this force now, or the topic on force. Force is said to be a vector quantity. Now we need to ask ourselves a question: what is a vector quantity? Now a vector quantity is a physical quantity. Now that's very important. We need to know that it's a physical quantity. Now this quantity will have magnitude and direction. Now magnitude is something to do with size. We're looking at how big this particular quantity is. Now when we talk of motion, we're saying that when forces act on an object, that object may experience motion. In other words, the object may start to move. Now, you would hear, or you would have understood me when I say forces act on an object. When an object begins to move, it doesn't mean that we have got just one force acting on that object, but there are a number of forces acting on it. But the effect of those number of forces acting on that object result in that motion. And now we are going to make use of an example of just two forces acting on an object. We know there could be a number of them. If you visualize an object moving on a surface like this one, you would know that when that object begins to move, there is a force of friction. There are maybe forces due to the air around that object. So there are a number of forces acting on it. But then the question is, what force causes that object to move? Now, if you look at the drawing that I have here, you would realize that I've drawn two forces. And because we are saying a force is a vector quantity, it has got direction, and hence we're making use of arrows to show in which direction these forces are acting. And if you take this central point to be representing your object, you will realize that we have got a force acting to the right. So let's call this one F1. We also have a force acting to the left. Let's call this one F2. F2 is not so clear, but please understand that. Now, these two forces are not of the same magnitude. F2 is bigger than F1. So F2 is greater than F1. Now, because F2 is greater than F1, it means that we are likely to see this object moving in the direction of F2. Now, what would have caused this object to move in the direction of F2? It is something we call resultant force. Now, I'll explain further what we mean by that. Now, this resultant force, we will get it making use of Now, this resultant force, we will get the magnitude of this resultant force by adding the two forces. In other words, we should be able to say, if I've got F2 and I add it to F1, what am I going to get? Now, we need to assign direction to this. You said, you heard me saying that F1 is acting to the right. Now, acting to the right and acting to the left in the situation of F2 here, it means that we can actually use directions or use signs to show our directions, to differentiate between right and left. So we have used a minus for left, we have used plus for right. Now, if we add them together, let's see what is going to happen. This will mean that F2 will be minus F2, and we're going to add it to F1, which will be plus F1. Now, because F2 is bigger than F1, you will agree with me that the answer we're going to get is going to be a force with a minus sign. And that minus sign in this case, in our situation, only means that the force is going to the left. And this force here, we are going to call it our resultant force. And this is the force that is causing that object to move to the left. Now, it is therefore important for us to be able to define what a resultant force is. Now, a resultant force is a single force. Now, that is very important. It's a single force that has the effect. It has the effect of a number of forces acting together. So it has an effect of forces acting together. You can have 3, 4, 5 forces acting together, but if you add them together, if you add those forces together, they are going to give you a single force, which will be a resultant. That will tell us in which direction is this object going to move, and with perhaps even the kind of acceleration we're going to get from that particular action of that force. So that's the concept of a resultant force. It is very, very important for you to know this. Now, let's look into motion in details. We have got quantities that we use to describe motion. One of the quantities that we use to describe motion is displacement. Now, the question is, what is displacement? Displacement is change in position of an object. Now, an object, to gain displacement, it needs to be changing its position. Now, let me just come up with some example here. Say you've got an object at a point A, and you have some point B there. And this object, due to the action of some forces, it begins to move in that fashion from A to B. Yes, now this object has changed its position from position A to position B, and the change in position is given by that straight line there, from A to B. Now, this straight line from A to B is the displacement of the object. Now, I will come back to this point here to explain to you what do we call this. I think you already have an idea of what it is, but later on I'll explain more what it is. Let me just mention it to you. This actual path that was followed by this object as it changed its position from A to B, we call it the distance. Now, that would mean this one, the straight line from A to B, we will call the displacement of the object. Now, that's one of the quantities we use to explain or describe motion. Let's come to the next one. The next one is a very important quantity. It's called time. Now, time, what we do with time is we say the time in which the object is in motion, that is the time we're looking at. In other words, if we look at how the object changes its position from A to B, and we are able to measure or time how long it takes to move or to change its position from A to B, then that time is the time in which that particular event occurred. We sometimes refer to this as the time interval. Now, you would know that we also talk, or we usually as well refer to it as delta t. The fact that we're using this symbol here, delta, we are actually saying that there is change in time. In other words, if you started your clock here at 10 o'clock, and when this whole event stopped from taking place at point B, your clock was telling you it's now 10:03. This would mean that the total time taken by the object to change its position from position A to position B is 3 minutes. So that is what we're talking about. Now, it means as well that we can't describe motion without bringing the time factor. We need to know how long certain events in that process of moving of an object take place. Now let's come to one other crucial, or rather important, quantity that we use to describe motion. It is a quantity called velocity. Now, velocity is defined as the rate of change of displacement. Now, I want you to focus your attention to this little word. It's very important, rate. Now, the moment a person begins to talk about rate, you must always know that something is happening per time. There is some event that is taking place, and that particular event is timed, or we know how long it is taking place. So when we say velocity is the rate of change of displacement, that would mean that we are saying this quantity here called velocity, which we may use v or small v for it, is mathematically given by delta x. Now remember, your displacement, we use delta x for it, divided by delta t. Now this is the rate. This is the rate at which displacement changes. Okay? And we know how much change in displacement we get per unit time. Now that is how we define velocity. And I want to move further here and talk to you about the units of velocity. Remember that displacement, which we use delta x to represent it, is measured in meters. So we have got meters here to measure displacement. The time is measured in seconds. So that S there is for second. Now this would mean that the unit of measurement for velocity is meters per second. That is very important. Now, if we are to move on now and talk about other quantities that describe motion, and we will be actually going back to something I referred to earlier on, which is distance. Now let's move on and look at another quantity that we can use to describe motion. And that quantity I referred to earlier on, it is actually distance. But then let's have a look at it, and we'll refer back to that diagram that I drew. Now, distance is one of the quantities that we can use to describe motion. You'll remember that I said we are saying the object is changing its position from position A to position B, and that is the change in position, which is called displacement. This. But then the path that the object followed as it changed its position from position A to B, this path is called the distance. Now, How do we then define distance? Distance is the actual path traveled by an object from its initial position to its final position. Right. Now, if we were to go back to the initial example and say the displacement delta x was 10 meters, and the actual path distance d was, say, 18 meters. And let's just assume that it took the object 2 seconds. So delta t is 2 seconds. Let's say it took the object 2 seconds. Let's say that it took the object 2 seconds to move from position A Let's say that it took 2 seconds for the object to move from position A to position B. Now the displacement was 10 meters and the actual path, which is the distance, was 18 meters. Now we can find the velocity of the object v. We will say velocity is given by delta x divided by delta t. What is our delta x? Delta x is 10 meters and delta t is 2 seconds. Therefore, our answer is 5 meters per second. So this means that the object changed its position at a rate of 5 meters per second. Now, in terms of the distance, what can we do from the distance? Now comes in another quantity that we need to talk about that is used to describe motion. And that quantity is called speed. Now, the speed of an object is the rate of change of distance. Now, see the difference between the two. There is velocity, which is the rate of change of displacement. Now we're talking speed is the rate of change of distance. Now, it means here we can be able to say, all right, we were able to get the velocity, which is the rate of change of displacement for this object. In the same way, we can also get the speed, which unfortunately we use the same symbol for it, v, but we know this time it's just speed, and we will say this will be given by delta d, which is the distance, divided by delta t. Now, what is delta d? The distance is 18 meters. And delta t, unfortunately or fortunately, it remains the same. And what is its value? It is actually 2 seconds. So we shouldn't be having that now. So what will this be? 18 divided by 2, it's going to be 9 meters per second. Now you will see that the unit of measurement for speed is the same as the unit of measurement for velocity, because you are actually dividing a quantity measured by meters in both situations. You are dividing, of course, by the same quantity, which is time, measured in seconds. But then the question is, what is the difference between the two? Now, the difference between the two will be explained in the coming section of the same lesson. Just listen carefully as we move on in this lesson. The last but very important quantity that I want to talk to you about, used to describe motion, is called acceleration. Now, what is acceleration? Acceleration is the rate of change of velocity. Now, look at how many times we've been talking about rate, rate. Now, understand this. I cannot overemphasize this. Every time you hear of the word rate, you must know that something is happening per unit time, or some event is occurring and you are actually dividing that by time, and in that way you are measuring how fast something is occurring. It could be the movement of an object like we're talking about here in this case, or any other situation where something is measured per unit time. So the word rate is used. Now, look, acceleration, and I'm going to use this part here to talk to this word here, acceleration. We're saying acceleration is the rate of change of velocity. Now, this implies that velocity is changing, and therefore, if something changes, we know it changes from one particular value to another. So we will refer to this as the initial value to the final value. So something is changing from one value to another. Now, it means we would be having a velocity changing from some initial value to some final value. Now, we will use v subscript f for final velocity if we are to find the change. So we are going to subtract the initial from the final to get that change. So we're taking away the initial velocity. But then acceleration doesn't just say it is the change in velocity. It says it is the rate of change in velocity. And therefore, this change in velocity has to be divided by time. And that actually is your equation for acceleration. So if acceleration, if certain object had or changed its velocity from, say, 2 meters per second to 8 meters per second, its final velocity would be 8 meters per second minus its initial velocity would be 2 meters per second. So that will give you the change in velocities. You divide by time. Say it took, again, say it took 3 seconds for this change to happen. So delta t is 3, then that will mean that you have got 8 minus 2, 6 divided by 3, and your acceleration is 2. Now, I want to bring something very important here. 2 meters per square second. Now, why is the unit here now being meters per square second? Why is the unit like that? We can explain it. We know that velocity is measured in meters per second. So the top part here, 8 minus 2 is meters per second, divided by delta t, it's time measured in seconds. So you have got meters per second divided by second. So you have meters per square second at the end. Now that is where that unit comes from. And it is very important for you to know and understand. Now, let's move on. Now, this is the part of the lesson where I said we will be able to show the difference between speed, velocity. Remember that. Now, remember when we started, we spoke about force and we said force is a vector quantity. And we said that a vector quantity is a physical quantity with both magnitude and direction. Now, here we are going to try and list 2 different types of physical quantities. These are vector quantities on the left, and on the right, we're going to have scalar quantities. Then the question is, what are scalar quantities? We now know about vector quantities. Now, scalar quantities are physical quantities with magnitude only. So I would write up there, magnitude only. So these ones, we just talk about how big they are. So we talk size when we talk about these ones. Here, we don't only talk about size, which is the vector quantities. We talk about both magnitude and direction. both magnitude and direction. And immediately we have said that force is a vector quantity. So it will be under this description or under this group here. And now, remember when we spoke about displacement, we said that it's change in position. Now, if something changes in position, we can be able to say with reference to its initial velocity, displacement, how far it is from that point. Is it 2 meters away from it? Is it 3 meters away from it? So displacement is also one of the quantities that has both magnitude and direction. So we can say for displacement, for example, that the object is now 3 meters to the right of position A or 10 meters to the right of position A. The third one that I want to put in is velocity. Now, what makes velocity a vector quantity? In other words, a physical quantity with both magnitude and direction. You'll remember that for you to get velocity, you are saying velocity is given by change in displacement over change in time. Now, displacement is a vector quantity, so dividing displacement by time does not change the nature of displacement being a vector quantity. And therefore, in that way, velocity is also a vector quantity. Now, let's look at the right-hand side column of this groups of physical quantities. Here we've got scalar quantities, and we're talking physical quantities with magnitude only or with size only. Now, I'm going to put here as the first one distance. Now, you remember in our initial example or drawing that we had, that the actual path followed by the object in changing its position from A to B was actually not a straight line. What was a straight line was the displacement, the change in position of the object. Now, that actual path followed by the object in changing its position from A to B is called distance. And as you look at it, you can see that we cannot tell with certainty the direction of the object at any given point of that process of moving from A to B, and that cannot remain constant. We can tell that at specific points, but we may not have that as a consistent value for direction from the beginning to the end. So distance has no direction. It is a scalar quantity. The next one I'm going to put here is speed. Okay? It's speed. So speed is a scalar quantity. It does not have direction, it only has magnitude. In the same way, we can say that we know that we defined speed as the rate of change of distance, so it will be delta d divided by delta t. Now, d, distance, is scalar quantity divided by time. Time doesn't have any effect in changing the nature of that quantity up there, which is distance, and therefore this remains a scalar quantity, right? There could be a whole lot of other quantities that we can list here. Down here on the side of vector quantities, we can certainly put acceleration here, because acceleration is also a vector quantity. Now, I would like us to move on. Like I said, you can practice and try to list as many quantities as possible from here, using the two columns here. But for now, that's the kind of quantities we're going to list. Now, let's continue trying to talk about describing motion. Right, so in describing motion, we do make use of different quantities like I explained, and having a look at what we have here, we are also saying an object can move in uniform velocity. Now, what does the word uniform mean? The word uniform implies that the quantity that is being referred to is not changing. So in this case, if it is velocity, it means that this velocity is not changing. Okay? So that is what the word uniform means when you read about it in text and other things in science. Now, when we have velocity that is uniform, it will mean that the object undergoes the same change in displacement in equal time intervals. Okay? And we are going to try and illustrate that making use of the graphs below. Okay? So these graphs now, we're going to use them to describe the motion here that we're talking about. If the change in displacement is happening in the same way within equal time intervals, what we would have if we were to draw a graph of displacement time or position time, okay, displacement time, it's this shape here. So this shape here will be that of a displacement time graph for a uniform velocity. Displacement is changing in a manner that it changes with the same quantity within equal time intervals. So we've got a straight line like that. And we are saying that here we've got a situation where the velocity is not changing. It is uniform. We can actually prove that by doing a simple calculation. If you check here, from time 0 to time 5 seconds, we had a change in displacement of between 0 and 10, or from 0 to 10. So we can say that given that velocity is change in displacement of...
Sorry, Tanika? What? Sorry, carry on.
Given the fact that velocity is change in displacement over change in time, we can then see that this would be 10 minus 0 divided by 5 minus 0. That is those are the changes, and then we will end up with 5 divided by 10, and that gives us 2 meters per second. Okay, so that becomes our velocity. And this velocity is uniform. Like I said, the word uniform implies that here the quantity is not changing. So if we were to move on to draw a graph of velocity time, so this is a VT graph, velocity graph, velocity time graph, you would see that the velocity is not changing, it is uniform. It's 2 meters per second throughout the period. Now, remember that with acceleration, we define acceleration as the change in velocity divided by change in time, so the rate of change of velocity. So acceleration is, this is rate of change of velocity, right? Now, is velocity changing? No. So if we were to calculate for the acceleration here, we would be saying that this change in velocity over change in time, it's actually the same as saying, look, it started from 2 meters per second. Even after 5 seconds, it's still moving at 2 meters per second. So you've got 2 minus 2 divided by the time 5 minus 0. So you've got a situation where you've got 0 divided by 5, and that gives you 0 meters per square second. So let's just write that better there. So 5 minus 0 equals 0 divided by 5, and that is, this equals 0 divided by 5, and that is 0 meters per square second, okay? And therefore, your graph of acceleration time, your AT graph there, is such that the line is on top of your horizontal axis there, or the time axis, in that way. We also need to know that an object can also move with uniform acceleration. And like I explained earlier on, what we mean by uniform acceleration, it would mean that we've got constant acceleration. In other words, acceleration here is not changing. Okay, so it stays the same throughout the motion. Now, when we have constant acceleration, what happens in terms of the graphs that we draw from displacement time, velocity time, ending up with acceleration time? You would note here, firstly, that if we look at the displacement time, okay, delta x time graph, okay, the xt graph here is not uniform. All right, you can see it starts slowly and then rapidly changing its displacement like that. In that way, we say the displacement here is not uniform. Here on the second one, you would see here we've got a straight line graph passing through the origin. In this way, we would see that the equal changes in velocity happens within equal time intervals, okay? So here, this will lead us to something else. It will lead us, if we were to calculate for the acceleration here, and you know that acceleration, and we know that acceleration is basically change in velocity over change in time, you would see that change in velocity here, and then change in time along the horizontal, actually it is the gradient of this graph here. It is the gradient of that graph, the m. So the gradient of this graph here gives us the acceleration. And because it's a gradient of a straight line, we know that it will be the same throughout the line. And therefore, acceleration remains constant. In other words, or making use of the terminology that we're using now, we would say that acceleration is uniform in this case. And therefore, if we then move on to draw an acceleration time graph, it would mean that that acceleration time graph would be such that you've got a horizontal line that shows that the acceleration is constant. And if we were to calculate for acceleration down here, making use of what is given to us, for example, the 20 meters per second there and the 5 second down there, it means that we'll say this will be 20. Remember that we're talking about change, and therefore, when we're talking about change, we need to show that we're talking change. So it will say 20 minus 0, because we're taking it from that point there, divided by 5 minus 0 for time there. And what do we get? That is 5, that's 20 divided by 5, and you have got 4, and you're calculating for acceleration. So that will be 4 meters per square second. Taking that to there to draw your acceleration time graph, then you have that shape of the graph there that tells you that the acceleration is constant or uniform. And that's how we define, or we describe our motion. We can use graphs, we can use quantities, we can put them together, and then we make sense of what we're talking about in terms of how objects are moving. Right. Let's now move on to something completely new now. Not completely new in the sense that it is not about motion, but that it's something that we don't normally bring when we talk about describing motion, but it is crucial that we talk about it. It is the question of momentum. Now, what is momentum? Momentum is something that any moving object will possess. So a moving object will always have momentum. Now, when we define momentum, we say momentum is the product. Now, this is very important. Now, this is a mathematical term, product. When we talk product in maths, we associate it with a multiplication sign. So that is an answer actually that we get from multiplication. So this is a product of mass and velocity. So when we multiply the mass of the object by its velocity, we get what we call momentum. We make use of small p as a symbol for momentum, and as we know that mass, the symbol for mass is m, and the symbol for velocity is v, p then equals m times v. Now from here we can tell the unit of momentum because we know that mass m is measured in kilograms. This is the standard unit of measurement for mass. And velocity, we were just working with velocity now. The units, it's meters per second. Now, what will be the units for momentum? Because we are multiplying mass by velocity, it would mean that the units for momentum, units for p, which is momentum, is kilograms multiplied by meters per second. So dot there for multiplication, meters per second. So the units in which we measure momentum is kilograms, meters per second. Now, earlier on, we said that when a resultant force acts on an object, we saw that when it acts on an object, the momentum of the object will change. Now, what do we mean by this? If an object was just stationary, not moving, okay, allow me to make use of my water bottle here. So if this object is stationary here, we know that momentum is mass times velocity. So if the mass of this object is, say, 10 grams, which will be 0.01 kilograms. To get its momentum, I would have to multiply its mass by its velocity. And unfortunately, as it stands there, its velocity is 0, and therefore its momentum will be 0 because it will be mass, which is 0.01 times 0, which is 0. So it doesn't have momentum. Now, if it starts to move, then its momentum is going to change. So that beginning of the motion is caused by a resultant force. So when a resultant force acts on an object, the momentum of the object changes. This change in momentum is brought about by the change in velocity. Because, and this is under normal circumstances, because under normal circumstances, the mass of the object does not change. So change in momentum, remember the small Greek word delta to mean change. Change in momentum is therefore given by the change in velocity. If the velocity of the object changes from v initial to v final, so the change in momentum will be given by, remember, it will be the momentum of the object at the final velocity, so v final, minus the momentum of the object initially, the initial momentum of the object. But m is common, so mathematically we can factorize it out, say v final minus v initial. So that's what we have, and actually that is the equation we have come to. Now this change in momentum is called impulse. It's called impulse. Change in momentum is called impulse. Now, we also need to know that impulse is also given by the product of this resultant force and the time that the force is applied. Now here, what we are saying is that this change in momentum, change in P, is also given or is the same as the product of the resultant force times the time in which the force is in action on that object. Okay? And remember, this whole thing again is given by m into v final minus V initial. So this is also very important for you to connect and understand. And you will see when we do some examples later on in this lesson why this becomes very important. Okay, now here are some other things that we need to know and use when we're talking about motion, more especially when we solve problems based on motion. It is equations of motion, and this is given to you, but we need to know how to use these equations, how to choose the appropriate one when we are answering questions. I'm going to use a question to illustrate what I'm talking about. Suppose here we have got an object. This is question 1. An object of mass 200 kilograms moving at 4 meters per second. This object changes its velocity from 10 meters per second in 2 seconds. Okay? It actually changes it from 4 meters per second to 10 meters per second in 2 seconds. Now, let's look at this one. Calculate the acceleration of the object during the first 2 seconds. Now, I'm going to use the top space for this. We are asked to calculate for acceleration. Acceleration is the rate of change of velocity. So it's V final minus V initial divided by delta t, the rate of change. This then would be equal to, we substitute into our given formula here. What is our V final? Our V final, let's go back to the information given to us. The velocity changed from 4 meters per second to 10 meters per second. So final velocity is 10 meters per second. 10 meters per second. Sorry. Okay. So 10 meters per second. And V initial equals, it changed from 4 meters per second. So the initial velocity was 4 meters per second. So when we are to substitute into our equation here, we know that V final is 10. So for VF, we're going to put 10 minus V initial is 4 meters per second. So we're going to put 4 for that. Then the division line. Delta t, what is our time? This process occurred in 2 seconds. So our delta t is 2 seconds. So for delta t, we're going to put 2 seconds. And what is our answer? 10 minus 4 is 6 divided by 2, right? Now this is 2 seconds. Here we know that the unit is meters per second. Then what is the answer here? 6 divided by 2 is going to give us 3. This will be 3 meters per square second. That will be the acceleration of the object. Right. Now, we continue in this problem, trying to solve it. We are also asked to find the initial momentum of the object. Now, I like the word initial. Initial means the earlier one. Now, for us to answer that, we need to go back to our velocities and say which one was the initial. Because remember that P, momentum, is mass times V. Now, the mass of the object is given to us. We can also add it into our list of given things here. It's 200 kilograms. So for M, we will substitute it for 200 kilograms. And then V, we know now this says initial momentum. So we'll say M times V initial. What is our V initial? It's 4 meters per second. So that will be 4. That will be equal to 200 times 4. This will be 0.008. So the answer will be 800 kilograms meters per second. Remember, don't forget the units of the quantity that you are calculating for. Right, let's move on to the next question. It says here again, calculate the final momentum of the object. Very nice one. Again, P final. Here we can also say P initial. P final will be given by mass times velocity final. That will be equal to, mass remains the same, it's 200 kilograms, times, what is our V final? Our V final is 10 meters per second, and therefore that will be equal to 2,000 times 10, and 200 times 10, and that gives you 2,000 kilograms meters per second. That's your final momentum. Now, here is a nice question, and I was very deliberate in this question to break it up in that way so that it helps you to see, because some of these questions may not be asked to you, but later maybe a question like 1.4 can be asked to you from you. But then you need to understand how you get there. Now let's look at 1.4. It says, calculate the change in momentum. If you have got your final momentum and the initial momentum, change will be given by final minus initial. I think that's a very straightforward one. So we can say that the change in momentum, change delta P, will be given by P final minus P initial. Yeah, someone might say, oh, we're seeing that for the first time. You didn't show us that equation. It's a very simple understanding here. I'm now just using the logic from the question here to say, if I am to look at the change, I've got the final and the initial, so it's easier for me to do that. So the final is 200 minus the initial, the final is 2,000, pardon me, minus the initial momentum is 800. Oh, sorry for this 8 here, 800. And this gives us 1,200 kilograms meters per second. Now, quickly understand that this change in momentum is still the same as m into v final minus v initial. And you use that, you will still get the same answer. And also understand, I'm just warning you, remember, delta P is also given by F times delta T. Okay, let's see. Maybe the last one is going to talk to that. Okay, now here is the last question based on this one, on question 1. It says, calculate the magnitude of the force. Yes, I was like anticipating this. Calculate the magnitude of the force. Now see, they say magnitude. They don't want you to tell them the direction. They just want you to tell how big this force is. Calculate the magnitude of the force that caused the change in momentum. How big is this force? Now, you would have to understand that to answer this question. F delta T equals change in momentum. M into V final minus V initial. So we know this, we have calculated this. This is change in momentum. So we can substitute straight away. We can say, all right, if we were to get the force, we can say that F then is equal to change in momentum divided by the change in time. Now, what is the change in momentum? 1,200 kilograms meters per second divided by time. Now, what is our time? We can quickly go back there. How long did this process take place? Right? This change in the motion of the object took place for 2 seconds, and therefore that is our time interval. We are going to use it down here. Where is our time interval? It is there. It will be 2 seconds. And then how big is this force now? 2 into 12 is 6. To the other zeros, it's that. So our force, the magnitude of the force, is 600 newtons. A lovely question. Right. Let's see if we can get to talk about another, or have a chance to look at another question. Let's look at question 2. It's an interesting one as well. A lorry travels in a southward direction at 12 meters per second. It then accelerates at 4 meters per square second for 200 meters. Calculate the lorry's velocity after traveling for 200 meters. Let's just write down what is given to us. We've got V initial. We've got V initial, and that is 12 meters per second. Okay, and then we've got the acceleration A at 4 meters per square second. Okay, meters per square second. And then we have delta x, that is 200 meters. Okay, and the question is, calculate the lorry's velocity after traveling for 200 meters. And therefore, what we're looking for is V final. Okay, and we need to choose the appropriate equation. The one that we need to use here, obviously, because we have got these quantities that we're having here, we even have displacement, it must have displacement in. V final squared will be equal to V initial squared. V initial squared. Okay, V final squared equals V initial squared plus 2A delta x. That's the one to use. Now, we can then substitute into this formula quickly to get V final. That is equal to V initial squared. V initial is 12 squared plus 2 times acceleration is 4 meters per square second times delta x is what? 200. Okay, so we can quickly find the answer to this. Let's see. Let's use our calculator for that. We've got 12 squared plus 2 times 4 times 200. Okay, and what's the answer? We've got 1744 is the answer, and you know that this V final will be the square root of that, so we'll just go ahead and say square root of the answer, and let's see what we get. And therefore, that's 41,76. So now the answer, V final, then equals 41,76 meters per second. So that's the answer there for 2.1. Now moving on, okay, we've got 2.2. It says calculate the average velocity of the lorry over the 200-meter journey. Average, when we have to get an average of something, we add them and divide by the number of quantities that we have. In this case, we've got initial velocity and final velocity. So we can say that the average velocity here, average velocity would be V final plus V initial, and then we're talking about 2 of them, so we'll be dividing by 2. That will be then 41,76 plus, if you remember well, our initial velocity is 12 meters per second. You divide that by 2, and what do you get? What is the answer there? Our average velocity comes to 26,88 meters per second. Okay, so that becomes the average velocity. Moving on to number 3, on the same example, it says calculate the time taken by the lorry to travel the 200-meter journey. We can make use of the average velocity to find our time there, because remember, from the average velocity equation that says V equals delta x over delta t, we can find what t is, which is, so delta t equals delta x, okay, equals delta x divided by the average velocity. And what did we find to be our average velocity? 26,88. So delta x is 200, okay? It's 200 divided by 26,88. That is the average velocity. And what do we get there? Can quickly make use of the calculator. So that is 200 divided by 26,88. And then we find the answer to be 7,44 meters per second. So the average velocity, I mean the time taken for the whole journey is 7,44 seconds. Okay, so that is the time. Alternatively, we can make use of an equation of motion. Remember now we have the we have final velocity, we have the initial velocity, so we can use the first one. V final equals V initial plus A delta t. So we can find or can calculate for t. What is our V final? We have found it. Our V final is 41,76 equals V initial 12 plus our A acceleration is 4 times delta t. So we can find delta t. Therefore, delta t equals 41,76 minus 12. What are we going to get there? Can work it out quickly. 41,76 minus 12, 29,76. All right? So 29,76, that is going to be divided by 4. And what do we get? 7,44. So that proves that our calculation is all right. Okay, so AT then equals 7,44 seconds. Delta T equals 7,44 seconds. Now let's move on to 2.4. It says draw a velocity time graph for the motion of the lorry over the 200-meter journey. And we need to be aware that here we're talking about a sketch graph, and therefore I don't have to draw it to scale. So let's just quickly, I'll just have my axis here quickly. So I have my vertical axis and I have my horizontal axis. On the vertical axis, this is a velocity time graph, so I will have my V, and this is in meters per second. Remember that you have to show in brackets the unit of the quantity in which the unit in which that quantity is measured when you're drawing your graph. And down here, this is time measured in seconds, so I will have it in that way. Now, from my calculations, the period or the time the lorry took to undergo the 200-meter journey, it's 7,44 seconds. So 7,44 seconds. Let me have my 7,44 seconds there. And we started looking at this this lorry when it was already in motion. Its initial velocity was 12 meters per second. So let me have my 12 there. And at the end of the journey, it was at somewhere at 41. Let me just get some space here. I'll rewrite that. It was at 41,76 meters per second. Okay, and so this is V meters per second. Okay. So I can then say, all right, when the time was 0, 12 meters per second was the velocity of the truck. But when the time was 7.44 seconds. Okay, the velocity of the truck was 41.76. So a straight line connecting those 2 points gives me the graph of the velocity time graph for the trolley, for the lorry. So this is a VT graph for the lorry. Okay. Now that was the last example we had time to work together. I would like to say to you, there will be more questions based on this from some of the resources that will be given to you, and also use other materials to practice this. From me, Tinjiko Kosa, thank you so much for watching. I hope you enjoyed the lesson and you really, really got help from it. Thank you.